Now, one more thing before we start to apply the Ohm's law. In the case of Gauss's law, you can know easily whether this charge is positive or negative. Just see what the sign of charge is. What about the current? When is the current positive? When is the current negative? Okay. The way we identify that is use the right-hand rule. Suppose the loop moves this way. Okay. You define a positive direction of the loop, which of course you can define it. If you define a positive direction loop, so in this case, you see the loop actually generally points in the same direction as the magnetic field. Therefore, you know this integral will be positive, right? This integral will be positive. So to preserve the same sign on both sides, we say this I enclosed is positive. So that means when a current flows in this direction, we should count it positive. If it flows backwards, we should count it as negative, because that will produce a backward running magnetic field. How to identify the positive and negative direction? Use the right hand rule again. Okay, use these four fingers of the right hand to turn around the current, to turn around the loop. I'm sorry, to turn around. If the loop points this way, okay, you curve around the loop, and if the direction of the current is the same as that of the thumb, that current should be considered positive. If the current actually flows backwards, it should be considered negative. Okay, that is how you identify positive and negative. So that is our discussion of Ampere's law. We didn't derive it, but certainly it is totally symmetrical with the case of Gauss's law in electricity. Now let's put it to test. Let's see whether it actually gives us the right result. Okay, we are going to revisit this problem. An infinitely long current carried by a straight wire. So we have this problem, which we actually did before. This distance, we call it A. Okay, we want to know the magnetic field at this point, right? You know, we went through all this integration to obtain this result. We're now going to use Ampere's law to redo the problem. Okay, to use Ampere's law to solve problems like that, we first have to recognize the symmetry of the problem. You have an infinitely long straight wire carrying a current. What kind of magnetic field would it produce? Well, it's going to produce magnetic fields in circular concentric loops, right? Concentric loops, and they are going to be centered here. Okay, so if I were to take a top view, okay, if I were to take a top view of the situation, imagine I look at it this way. Okay, look at it this way. Then the current would just be a dot penetrating out of the paper, and surrounding it would be magnetic field lines. You get a magnetic field lines like this, and they point this way. Okay, they turn counterclockwise like this. Because of the symmetry of the problem, everywhere on a circular loop, a certain distance r from the wire, we know that first of all, the magnetic fields are all tangential to this circular loop. Okay. That's one. And secondly, they all have the same magnitude. They all have the same magnitude. This is the symmetry of the problem. Okay, so we have a whole bunch of concentric loops forming the magnetic field distribution. In order to find the magnetic field at this point, when I want to choose an Amperian loop, this particular contour, that contour certainly has to pass through that point. Okay, that's one thing. But that contour also, you want to choose it so that it reflects the symmetry of the problem. So tell me, what kind of shape will be the contour that you're going to pick? Okay? How about picking up, as you suspected, we're going to pick up a circular loop centered right here. Okay, and the plane of that circle will be perpendicular to the current. So the current really is on the axis of symmetry of that circle. So we have a circular loop like this. Okay, we're gonna choose a circular loop like this, right? That would be the choice of an Amperian loop. You can choose any loop you want, but that choice is the smartest one because it gives us full utilization of the symmetry of the problem. Because of the symmetry everywhere on that particular Amperian loop, the magnetic field all points tangentially, and they all have the same magnitude. Okay, they all have the same magnitude, including the magnetic field at point P. So, how would I use Ampere's law to find the magnetic field at point P? once you choose the correct Amperian loop, this becomes a piece of cake. Watch. I start with B dot ds for this particular contour. Okay, let's see what is that equal to. First of all, we know that B and ds, they point in the same direction, right? We define the contour direction to be like this, following the direction of the magnetic field for simplicity. So B and ds have the same direction because B is tangential by symmetry. So that's the first step, B ds. That's it. The angle between B and ds is 0 degrees, so cosine 0 is 1. Next, we also realize that this B, this is the magnitude of B, it's the same throughout the entire contour, so we're going to take that out. Okay? Now, this is the integral over all the length of the segments for this entire circle of radius A. Okay, so how much is that equal to? Just 2 pi, right? Circumference. But wait a second, what do you think that should be equal to? Shouldn't it be equal to I enclosed times mu naught? That's Ampere's law. I enclosed, there is only one current right here, that's I. So therefore, you can solve for B now. B equals mu naught I over 2 pi A. That's it. Okay, see how simple that calculation is? Now you compare this with what we got before. I mean, we got the same expression before in a previous page. Okay, let's see. Where is that? Right here. See that? That belongs to the previous lecture. We went through this whole, integration, differentiation thing. We got the same result, mu naught I over 2 pi. But now, we get the same answer with much greater ease. That is our first example testifying the power of Ampere's law. Now, if we continue to observe more examples of cylindrical symmetry, which is a very common symmetry when it comes to current distribution, let's look at our next example. Okay, it's just slightly more involved than the previous one. We do not have an infinitely thin wire carrying the current. Okay, this wire is now expanded into a cylinder of finite radius r, but it's still infinitely long, and there is a uniform current distribution over its cross-sectional area. Okay, the total amount of current is I, distributed uniformly over its surface. Now what I want to know is, what is the magnetic field everywhere in space as a function of r, which is measured perpendicularly from the axis of symmetry. Okay, now even though this is more complicated than the previous problem, the setup is still cylindrically symmetrical, which means the magnetic field should still observe the same type of symmetry, right? The magnetic field lines will still form concentric circles. Everywhere on the same circle, centered right here, the magnetic field lines, first of all, are all tangential, and secondly, they all have the same magnitude, right? So if I were to draw such a magnetic Amperian loop centered right here of radius r, I would still get the same deal. B dot ds equals 2 pi r times b. It's still the same as before. Okay, but here's what's interesting. The right hand side is mu naught times I enclosed. In the previous case, I enclosed was just the current I at the center. But now, things are a little bit different. It depends on how much r is. R is the distance between the point of interest and the axis of symmetry. If this r is less than the radius and more than the radius, the answer will be different. Okay, if it is more than the radius, then you're looking at the magnetic field lines outside this cylinder, right? So how much current do you enclose? Well, you draw an Amperian loop like that, you enclose everything. You enclose the entire current, right? So if you're looking at the magnetic field lines outside, you just replace I enclosed with the total current I. You just get the same result. If r greater or equal to the radius, then I enclosed simply equals the total current I, and therefore BR would then be equal to mu naught I over 2 pi r. That's it. That is the same result as before. So you cannot tell how thick the cylinder is, okay, if you're outside it. This is similar to the case of electric field of a uniformly charged sphere. In fact, if you're outside that sphere, you will see the same exact field as if that sphere were a point charge at the center, or as if that sphere were hollow. Yeah, you cannot tell what kind of charge distribution you have as long as it's spherical symmetrical. You just enclose the total charge Q. Same deal here. You don't know how thick that Y is, as long as this, you don't break cylindrical symmetry. But things get more interesting if you dig a hole and go into it. Okay, so you're here. If you're here, the Amperian loop, which is still a circle, is now smaller than the perimeter, and therefore you're not going to enclose all the current anymore. Let me draw a top view. You're going to see something like this. Here is a top view. Here's the center of symmetry, and you're looking at a point P here, right? You need to draw an Amperian loop like that to apply Ampere's law. So this is R, and that is all the way to the edge of the cylinder. You only can count the current that is enclosed by this Amperian loop, and therefore only the current flowing through this cross section, not the entire cross section of the cylinder. How much current is enclosed here? Okay, if R is less or equal to big R, then I enclosed equals what? It is a fraction of the total current. Okay, the total amount of current going through this entire cross section is I. But the current that is enclosed by the smaller loop is only a fraction of I. What fraction? Because current is uniformly distributed, that's our assumption, over the cross section. That fraction is just a fraction of the cross section area, right? It's just this shaded cross section area divided by the entire cross section area. So it is just pi r squared over pi big R squared, right? That is the amount of current enclosed by this smaller loop, and then you have BR equals to what? Mu naught 2 pi r I enclosed. You plug the I enclosed here, what do you get? You get mu naught over 2 pi, and then what? There is an I here. Okay, pi and pi cancels. Small r squared cancels with 1 power of r, but there is a big R squared, so it's like this. Okay, so in other words, you get a linearly increasing magnetic field as you go out. It is very much like the case of a uniformly charged cylinder. Infinitely long, straight. The electric field, if you follow Gauss's law, you also see that it is uniformly, it's a linear function. It grows linearly, and then when it's outside, it goes like 1 over r. It's just the same as that. Okay, there is a complete analogy. In fact, if you were to draw the magnitudes of the magnetic field line as a function of r, and here this is the radius, okay, this is the surface of the cylinder, then inside of it you get a straight linear function, that's that, and outside you get 1 over r. It goes down like that, okay, goes down like that. As a matter of fact, you should expect no discontinuity between these two expressions at that point. It should be continuous. Why? Because in the case of electricity, as long as you do not cross a two-dimensional charge density, you will not see a jump in the electric field. Here, the source is no longer electric charge, rather it is current. So as long as you don't see a two-dimensional current distribution pressed into an infinitely thin layer on the surface of the conductor, you are not going to encounter a sudden change in magnetic field. And in fact, you can see here, when you replace big R with small r, okay, so you're right on the surface, okay, replace small with big R, that is, you're right on the surface, you have mu naught over 2 pi big R, and here, let small equal to big R, you have mu naught I over 2 pi r, 2 pi big R, they're equal to each other, okay, there is no discontinuity. So that is an important example of the application of Ampere's law. Now, we can make things a little bit different if I allow all the current to flow only on the outer surface of that cylinder. In other words, it's a hollow cylinder. It's not uniformly distributed current. It's only on the surface. But on the surface, we assume that the current flows uniformly over the surface. Okay, so you still have the same, cylindrical symmetry, but the current enclosed will be different once you dig a hole. Now, all the currents are now flowing on the surface, right? So outside, you still enclose all the current, but once you dig a hole, you go inside. How much current is enclosed on by this ampere loop? 0, right? So you should replace I enclosed with 0. So once you're inside, what is the magnetic field equal to? It becomes 0. Okay, so now there's a sudden jump in the magnetic field. It remains 0 inside, but right across the surface current, it jumps to that expression, mu naught I over 2 pi r. Please consider the analogy of that hollow cylinder with the case of a hollow cylinder carrying a uniform surface charge density. The electric field had exactly the same situation, where if you go inside the cylinder, the electric field was 0, and right outside the cylinder, the electric field goes like 1 over r. It's just analogous. Okay, now one more example. We're going to fully exploit cases of cylindrical symmetry. Okay, here's a practical example, something we use quite often, a coax cable or coaxial cable. What is that? That is a way of forming a current and take that current to an electrical load such as an amplifier, receiver, whatever, but you allow the current to flow back in the same wire. Okay, now instead of forming a current in this wire and another returning current in a neighboring wire, we are going to put one current at the center of a cylinder, and then we have an insulation layer, or you can think of it as vacuum if you want to, and there's an outer cylinder, okay, made of conductive materials, which is concentric with that inner wire, and in that outer cylinder the current flows backwards. Okay, that's in order to put the return current on that outside cylinder. And in between the wire and the cylinder, you can consider it's made of insulation material or vacuum. That is called a coaxial cable. It's coaxial because the cylinder, the conducting cylinder, and the conducting wires have the same axis. Okay, let's look at the magnetic field anywhere as a function of r again. Okay, you have two regions in space, inside and outside. Right? And since you still have the same cylindrical symmetry, you still have the same formula, and that is B as a function of r always equals to mu naught I enclosed over 2 pi r. It's the same thing. Okay, again, the only difference is how we calculate I enclosed. Now this time, if you're inside, okay, do you still enclose nothing? Oh, not true. You enclose I, the current I, right? So I enclosed equals I if r is less than what? I is less than, r is less than the radius, right? But once you're outside, okay, you get a loop like that, right? What's the total current you enclose? Well, you got a current flowing out, you also got another amount of current flowing in, that's from the outer side. The total current is 0, okay? So that is different from before. You plug these into here, you'll find that B as a function of r is now, plug that I in, mu naught I over 2 pi r only for the interior. But it drops abruptly to 0 outside. See? Okay, so the magnetic field will now look like this. B as a function of r. It looks like this. At the surface, it abruptly drops to 0. Okay? It's like this. There is now a discontinuity on the surface as it crosses the surface. Now, first of all, you probably can see why we often use a coaxial cable to carry electromagnetic signal. It is because the magnetic field outside of the cable is 0. So all the magnetic fields created by all these currents cancel each other out once you're outside. So this cable does not introduce an unwanted magnetic field outside of it. Okay, it does not leak out that way. That's an advantage. It's better than an arrangement like that where the magnetic field outside is not quite going to be 0. That's one thing. Another thing is, why do we see a discontinuity in the B field? Okay, you see, whenever you see a discontinuity in an E field, the electric field. That is because you have just crossed a two-dimensional current charge distribution. Right? You press charges three-dimensional into an infinitely thin sheet, and you get sigma current. You got what's called surface charge density. Okay, here in the magnetic case, we're gonna replace charges with currents. Okay, and instead of three-dimensional currents, we press the current onto a thin sheet. We get what's called a two-dimensional current distribution. And every time you cross a two-dimensional current distribution or surface current, you will see a sudden jump, a sudden change in the magnetic field. And that is exactly what we're seeing here. Okay, that's exactly what we're seeing here. There is a sheet or two-dimensional charge distribution, current distribution. As you go across from here to there, there is a sudden change in the magnetic field. So that is expected. Okay.